Okay, we're going to do 221. Here we're going from a velocity graph to a position graph. We're also calculating total displacement and average velocity. Alright, so what we're doing to get from velocity to position is to look in each section and find the area under the graph. That'll give us the displacement. So in the first section, the height of that rectangle is 1 meter per second. And the length is 4 seconds, so the area is 4 meters, which is the displacement. So if I started at 3 meters here, which is what I was given, you can't figure out where the initial position is from the velocity graph only. You have to be given that info, or make it up. So if I go up 4 meters from 3, I get to 7. I know it's linear because it's CVPM. The velocity value down here doesn't change, it's constant, which tells me the slope of the position graph doesn't change. So if the slope doesn't change, that means it's linear. Alright, in the second area, I have a rectangle. The height of that is -2 meters per second, and it's 3 seconds long. So that tells me the delta x in that region -6 meters. If I started at 7, I came down 6. That's going to put me at 1 meter. And we had a direction change there, go from positive to negative velocity. In this rectangle, it's 2 meters per second tall, but it only happens for a second, so I get a delta x of 2 meters. I started at 1, and the next second I'll be back at 3. The next area, I have no velocity here, so there's no area to compute. So delta x is 0. I don't go anywhere. So that's why my graph has a 0 slope. Okay, so I started at 3 meters. I ended at 3 meters, which means my delta x final minus x initial, 3 meters minus 3 meters, I didn't go anywhere. My average velocity, delta x over delta t, or the slope from the first point to the final point, also 0. We had one more direction change we didn't circle. Okay, on to the second one. Again, we're looking at areas. So if I look at the area in this first segment, it's a rectangle, -2 meters per second for 3 seconds. So my displacement is -6 meters. For that section, I started at 8, so displacement of -6 would put me at 2. Again, it's linear because it's CVPM. This value doesn't change, so the slope doesn't change. It has a negative slope of -2 meters per second, so that's my value here. In this next box, I have -1 meter per second as the height of the box for 2 seconds. So -2 meters is my delta x. So I'm going to go down a further 2 meters in the next 2 seconds, which puts me at what we've called 0. And in the last 5 seconds, I go 1 meter per second for 5 seconds. Gives me a delta x of 5 meters. I started at 0 at that point, so over the next 5 meters, next 5 seconds, I end up at 5 meters. So I started at 8 meters, I ended up at 5. xf minus xi is 5 meters minus 8 meters, -3 meters. My average v, which is delta x over delta t, or the slope between these, is -0.3 meters per second. This is -3 meters over 10 seconds. I did have one direction change here where the velocity changed sign. Over here where my average velocity was 0, my average speed was definitely not 0 because I did have significant distance traveled. So the average speed is distance traveled over time. See, I traveled 4 meters plus 6 meters plus 2 meters, which would be 12 meters. Total distance traveled over 10 seconds would be 1.2 meters per second would be the average speed, but the average velocity is 0 because the displacement is 0.